All right, this next talk is about running jobs, and I am going to have to go through it pretty quickly, but hold on, let me. All right, this is the one where I need to keep track of the time, so I will look at that. Okay, so this one is where we're just going to go a quick overview on many topics. Compiling and linking code. If you've done any programming, then you know you have, like, even with Java, Python, C, then you have to compile and link it. So I'll give you some basic overview on that. And the information in my talk is very heavily synced with the information in the user guide. So this is just a quick highlight, and then you can go back into the user guide and the Expanse 101 hands-on tutorial to kind of put the pieces together. And then I'll talk about running jobs using that batch scheduler, so that switch device that gets you onto the different nodes, and then a couple of basic examples: MPI, OpenMP, and hybrid, and then some final comments. We may not get through all of these, but you'll have the example to inform you on how to get things done. Again, there's a picture of Expanse, the architecture, and a little more detail here. And again, we'll go into it in much more detail here in the next week. But the scalable complete unit has a high-speed switch. It has 4 nodes, 56 compute nodes, and 3,584 CPU cores. It's got 4 by 4 GPU nodes, 10,000 tensor cores, and 256 cores down here. So the idea is most of the jobs that we envision running on Expanse should fit on one of these racks. And if you can have everything closely located, then you minimize communication time. And so that's the goal with these SCCUs. And I think we've added a few more. And so there's 13 or more of these. And we have a 12 petabyte Lustre file system. We have a Ceph object storage system, high-speed networks connecting them all, and a management rack. And the thing now is, these days, HPC systems are liquid cooled. That's an evolution from the 90s where everything was cooled. Then we went with commodity and using air cooling, and now we're back to liquid cooling. My son has a liquid cooled video gaming system on his desktop at home. So it's becoming more common. All right, let's look at compiling and linking code. So there's CPU and GPU nodes. And for CPU, we have the full suite, GNU, and we have GNU, Intel, AOCC. AMD has their own compiler, and there are some cases where it might be the preferable compiler. You really have to experiment with the compilers to see which one is best for your application. There's cases where GNU outperforms these very expensive high-end Intel and AOCC compilers, and there's times when the only thing that will work for you will be the AMD. So you'll have to experiment as you migrate your code onto the system. It's very normal, but you should play with them all and work with them and see which one is the best. We have multiple MPI implementations: OpenMPI, MVA Pitch, and Intel MPI. And again, a majority of our applications are built with the GNU public open source GNU. And so that's helpful. In one aspect is, if you think you might be running on a large suite of different HPC systems, then if you have a common compiler, the likelihood that all the features that you're using are available on all the different systems you want to run on will be high. And so it'll be easier to port your application around. And then there's Intel and AOCC have flags to support the advanced vector extensions, which give you a higher performance. And we'll talk about that next week in our performance sessions. For GPU, we have GNU, Intel, and PGI. And the Expanse login nodes are not the same as the GPU nodes. So when you go from CPU to GPU, make sure you load the right module environment, because the module environment you have set up on the CPU system does not propagate down to GPU. You have to make sure that you load all the modules. So our pattern is that you load the modules and you put that into your scripts that you use to run your jobs. Okay, so just a quick overview. In the user guide, you'll see these tables. The user guide is always much more updated than my talks, so this is for reference. And all the compilers, we have a table, and the pattern of the table is the types of languages. And we do support Python and Java, but they're not on these tables. And we have the serial command, the MPI, message passing interface command, the OpenMP. So MPI is used more for communication between nodes, and OpenMP is threads based, so it's often used for acceleration on a node. And then you can do hybrid MPI plus OpenMP or other hybrid models. And so these are the commands you might have to pass the OpenMP command here. If you want to use AVX, Advanced Vector Extensions, add this argument to your compile command. And there are examples in the user guide. And then if you want more information, you can type that command down below. So you'll see this pattern all through the user guide. To use the compiler, first thing is I don't know my environment, so I purge my environment. And then I load specifically, here's my recipe to make sure I can use the GNU compiler. Okay, this similar for the AOCC compiler. Same languages. Notice the commands though are a little bit different and require a different name and argument. So you really want to make sure you keep track of those. And you have to load that module. And for example, if you had an Intel compiler and you try to load that, the module system will tell you, hey, there's a conflict. And sometimes that's why the pattern we recommend is purge, clean it up, reset, load specifically what you need, especially if you have to change between compilers, because you won't be able to compile or run successfully if you're trying to compile with different links to different libraries compiled by different compilers. So again, here's an example of using the AOCC compiler module list. Here's what I've got. I purge, I list, I don't have any modules. I load Slurm, CPU, Intel, OpenMPI, module list. I've got all these modules and it was like, oops, I want the AOCC. So you can do something cool called module swap Intel for AOCC. Now, if you're getting really picky, you may have to actually explicitly pick the particular version of a compiler that you want. But due to I go ahead and I run this command and I get back a message, due to module path changes, the following have been reloaded. So the system for me figured out I need a different OpenMPI and it fixes that. Now I listed, I've got Slurm, I've got CPU, I've got AOCC, OpenMPI, and I can find MPI run as a common parallel job launching command. And you can see that it's in a particular path that you can tell that this is a different path and you would find a different one if you had loaded Intel. So it's very informative when you can figure out and remember to run these commands. But you can see why having a recipe, I keep little text files. If I'm not writing a batch script, I just keep little information files on my recipes. We recommend that you put them in the batch scripts, and I'll talk about that in a moment. So this is the Intel compiler for CPU and GPU. And then using the Intel compilers, it's very similar. In this example, I came in with a default, or this was the environment I had before. I purged it, I have no modules. And to demonstrate, I type which MPI run. Now I can't find it. So now I'm going to load the Intel and the OpenMPI and list. There's my modules. And now I find which MPI run. So now I can find that command. The which command is great. It tells you where a command is located. And notice how this path here is different from the path before to MPI run. And so you can verify that you're getting the right one that you need. Okay, so you can access specific Intel compiler features for accessing libraries and getting acceleration in your code. You may not need it. You have to look into that, and if you have to ask consulting, go ahead. You also have access to the Intel Math kernel libraries. They're very well-known libraries, and they have optimized commands and subroutines that can give you very good performance for matrix multiplication and other command applications. Okay, PGI, that's only on the GPU, but we do have the PGI compilers. Okay, so if you're on a CPU, then you would do the same thing to use the PGI compiler. All right, running a job. So there's different kinds of jobs that you would run. First of all, where are you running them? On your command line, on your laptop. But if you're on an HPC system, you're talking about parallel applications, and there's two basic parallel models that I'll talk about today. There's more complicated thread-based models, but today I'll just talk about the distributed memory and the shared memory model. So in distributed memory, this is where we would be using something like the message passing interface. The devices are discrete nodes. For example, the nodes on the expanse rack, and they don't share any memory. So if you update some data on this CPU, you have to go out to a network and send data to the other CPUs or nodes and share your data that way. So services-oriented architectures, MMOs, and peer-to-peer applications are other examples where you have something running on an isolated machine, and you have to share data by sending data through a message. You're sending messages when you go onto the web browser and type https google.com. You're sending a message across the interconnection network to Google and getting information back. So that's the distributed memory model. So in other words, for the different processes in our perspective from HPC, these are different nodes on the expanse rack. And if you're doing a very large computation where you need a lot of nodes, then they have to, like you're looking at fluid flow along the California coastline, then San Francisco needs to get data down to LA. This model is running, this part of the application is running for LA, and this is San Diego. They'll have to send data and share. And that's great. You can get your results. The message passing is accurate and well understood, but it can cost you time. So the other model, though, is what we call shared memory, where these would represent cores, for example, on one of the AMD EPYC nodes, where we have 128 cores. They're still running independently and in parallel in most cases, but they have a high-speed interconnection network that allows them all to access memory that's right there on that node. And so you have less contention, and it's a lot faster to move your data around. If you have an application that's doing a lot of data I/O for the calculations, then you get a lot better performance. So shared memory is for one particular type of application. And so in this case, we call it SHMEM, shared memory. So you have coordinated communication between all the tasks, and they all share the same memory. And at some point you get to where optimizing your code, you're worried about how long it takes to move a little bit of data between the CPU and the local caches. We won't go into that today, but when you're really at that point where you're optimizing your code and trying to cut it down from taking a year to 1 month, then you start looking at these details. So you can use uniform or non-uniform memory access, cache-only architectures use this. Most common HPC HPIs for using shared memory, would be like an OpenMP, and we'll talk about that. There's the threads that are used on HPC systems come from the POSIX standard, the Portable Operating System Interface, and these have been around for ages, and they're part of what make even your laptop work. But they're optimized now for parallel computing, and Open Multiprocessing, OpenMP, uses POSIX at the base of it, but it's going to be a little more advanced and optimized for CPU computing, excuse me. And they're optimized for parallel computing, which have different requirements than optimizing the ability for me to run 85 applications on my laptop. Right now, I've got about 15 different applications running, like, 15 browser windows. I've got PowerPoint running, Word, a lot of different applications. Those are also kind of a shared memory model on your laptop, but the requirements are different than high-end parallel computing. So to run jobs on Expanse, you would use the batch mode, and to get onto those compute nodes. One way is with the batch node. So you'll submit the jobs to be run on these compute nodes using the sbatch command. So now we'll start looking at what that means and what is a queuing system and the architecture for controlling access to those nodes. Computationally intensive jobs should be run only on the compute nodes, and we have limits for the number of jobs you can queue up and run based on your allocation and the partition you're going to pick. And note that submitting a large number of jobs can impact the overall scheduler response for all users. And this is a big thing. We're going to talk about that next week in the data session. Is a lot of CNN applications that do a lot of image processing. Sometimes you guys will bring, those of you who do this will be bringing down the network because you're moving thousands and millions of little files at a time. And so we want to help you optimize your batch scripts for that. So batch jobs, the methods for running are batch jobs or interactive jobs. Batch jobs are going to go through that queuing system, and for us, we use the Slurm, the simple Linux utility for resource management, Slurm batch environment. Futurama fans, yes, I've confirmed it on many sources, even on the Slurm site. They did name it after the Futurama Slurm drink, and the last time I went to supercomputing, they were giving away cans of Slurm sodas, and they're awful, but it was pretty funny. But yes, in case you're wondering, it is named after Futurama Slurm. So the system, all those thousands of nodes that we've got get broken up into different virtual partitions that are managed by the queuing system, and then there's a time limit for the run on the system, a maximum of 48 hours. If you need more, work with the support staff to find out whether or not they can arrange that. Most likely they can, or whether you need to be moving to a bigger system. And then you'll specify the number of nodes and the tasks per node. For example, if you get one node, you could have up to 128 tasks on that one per core. And then how much memory you require, if any. If you have a Epic node, it has a maximum memory on the node. And if you need more than what's on that node, you would then need multiple nodes, for example. You'll give the job a name and an output file location. Maybe you want to get an email a message when the job is done, and then you'll include some configuration information. All of these will go into the batch script, and I'll show you examples. And then interactive jobs. You might be in a scenario where you want to run the job on the node, but you want to have a hands-on, get on that node. Then what we do is we have a way for you to request to get one of those nodes and be logged onto it and work on it interactively. This is great if your compiling takes a long time, or if you want to test out a Jupyter notebook, for example, or run a MATLAB application or something like that. But we let you do those on the interactive nodes. And I'll show you an example of that. And this is also explained in the user guide. Okay, so what is this Slurm resource manager? It's a large system that, remember that architecture diagram I showed you? You're the user on your laptop, you SSH on, and you're on the head node. And the gateway to all of these thousands of compute nodes and cores is through this switch here. And in that, I show it as a little box, but it's much more complicated than that. But all you need to know is you're going to write a batch script, use a Slurm command to submit a request to the batch manager, the queuing system, and it'll get processed for you. And a short time later, you'll be given a job ID, and then the Slurm system will wait until the right number of nodes and cores are available for your job specifically, and then assign a set of nodes and resources for your job and start your job running. And that can take a while. It depends on how busy the system is. And so, without going into too much detail here, I just want you to have a feeling these yellow boxes kind of represent the services, the servers that are running. And these are your user commands where you'll communicate with the Slurm daemon that will take your batch job request. So srun will launch a job or send a request to run a job, and sq will tell you how many jobs are running, and I'll show you some examples of a few of those. And then there's all these daemons that are running to control and integrate and coordinate all these nodes. So the common commands as some examples is sbatch, mycode.slurm.sv. This is just an example of a name for a batch script. Typically, our convention at SDSC is we call them SB. I've seen people name their batch scripts with a BAT. You can name your script whatever you want. Just make sure you know what it means. So our convention for training is a .slurm batch SB. That way I know this is a batch script. It's not an executable. It's not my Fortran code or my Python code. That's the batch script I'm going to use to get a job to run. When I run this command, if everything is good, and the Slurm scheduler will parse your batch script. It's a Unix type of batch script, shell script. It will parse it and make sure everything makes sense. If there's an error, you'll get back an error and no job will be submitted. But if everything is good from the perspective of the Slurm scheduler, then you'll get back a job that you can monitor. So sq-u user, this would be my user ID, and I get back information on that job that tells me it's pending. So I wait and wait and wait, and sometimes I wait a really long time, but once it's running, I'll have this R state running. And I can cancel a job if I go, oops, I used the wrong code. And the my code happens to be the name of the executable that I want to run. And so this is the different partitions. So they've taken that large machine and broken it up into logical partitions with different configuration limits. And so there's the compute and shared. Shared means you'll get a node and you don't care if other jobs are running on the cores that you're not using. So maybe you're not trying to get optimal performance, or you don't need all that memory. And it's cheaper to run a job on shared. You use fewer of your SUs. Excuse me, and they have that for GPU shared, large memory nodes, but you'll get charged at a different rate. There's a debug node. This is a great partition to use because it's very quick. Jobs can't run very long, so even if a lot of people are trying to debug and test, is what it's designed for, you'll still get your node pretty fast. And preemptive and GPU preemptive, you'll have to work with the team to get those. Here's an example batch script. So in my Expanse 101 HPC training examples, I have a bunch of example code based on a lot of what's already on the CM shared directory. But this one shows you the structure of a batch script. So when you see pound sbatch in all capital letters, that's an instruction for a directive for the Slurm scheduler, as opposed to echo Slurm job name. This is a Unix command. And so this is just a little script that is simple to understand. You're not trying to run anything advanced. And it's a great kind of a pre-hello world to make sure that you can launch a job and your environment is set up right. Notice I put in all the environments that I want. I purged to get rid of anything that might be there to cause a problem. And I put in my recipe. We really strongly recommend that you always get in the habit of explicitly loading in your environment. And then the job name, I can call it what I want. This is an example for calculating prime numbers. And I give it an example for the output name, MPI prime dot %J %N. So this is the job ID and the node number that the job ran on, which sometimes really helps you figure out what's going on with your output. And here I'm using the partition Notice I commented out the S batch. If you're going to put comments in there, like around a line with S batch, use a bunch of those hashtags because Slurm loves it. It sees pound hashtag S batch and it wants to do something with it, but several hashtags and it will ignore that line. So here I'm asking for one node and just one task. I'm going to export all the data out. I'm putting in a time limit of 10 minutes. I probably only need one. The smaller your time limit, by the way, the more accurate that is, the higher the probability is that if I have a 10-minute or a 1-minute job, the scheduler will backfill my short little job in between other jobs that are bigger that are waiting for all the nodes that they might need. So it's a good way to sneak your jobs in. And then you need, that's the account and that's the account number. You can't use this one, it's just there for an example. You're not allocated on this, but you would put in, for example, the training account number. All right, here's the environment, and I'm going to echo, there are some already predefined Slurm environment variables. So one is job name and job ID, and so I just print them out. Then I echo the date. And so here I'm in my folder, Calc Prime. I submit my SBatch job ID, my SBatch, and run the batch script. And this one I'm passing a variable to it. And I think that example is in the next slide, so I'll get to that. But I get back a job ID. I look for my jobs. There it is. It's running. It ran quickly. And so here's my output file that was created, the name, the job ID, the node it ran on. I made that that file name up in this command line right here. And then Slurm job name, environment, the host name, the date, who am I, what working directory am I in, so a lot of information gets printed out here in this output file. Okay, so Slurm has environment variables. If you know Unix, you know what those are, and you can go. I've put the links in here so you know exactly where to go in the really large, informative Slurm website. But you can look and get the different ones, and you're welcome to pull those out. These are going to be occurring once the job starts, and then there's other output environment variables. So take a look at those, and they can really help enable some of the work you're trying to do. For Slurm, use the export flag if you want to pass values into the batch script. And I'll show you a complete example in the next slide or two. So you can pass two variables, x and b, dash dash, here's the example, sbatch dash dash export equals x equals 7 comma b equals my string. You can make as many variables as you want in the command line argument. It's great for parametric scaling. And then there's the name of my script. Or you can use the export all to get other environment variables. So your environment variables will be passed into the script. Move along here. So here we are looking in the same kind of script, but here I'm going to use that environment variable that I'm going to pass. It's called nlow, and I'll echo the variable value of nlow. And here I export nlow equals 1000. And so it gets printed out, and I look for prime variables for some variable, n high and n low. N high is printed by the code, not my script. I didn't print n low here. All right, so you can pass variables, which eventually you'll get to think, oh, that's pretty cool stuff. All right, so the srun command. You can run jobs from the command line using srun. This allows you to launch a parallel job. There is MPI run and srun. So srun is used by Slurm to launch a parallel job. We recommend you use srun because it's customized and optimized to run MPI jobs and parallel jobs by the Slurm system. It will, if it needs to, it will create an allocation to run the parallel job. You can pass common arguments to it, but the big difference is MPI will work, but it might not work optimally. MPI is not optimized to the Slurm system on Expanse, but SRun is. And Mahidar and Marty and the user support team do a lot of work to make sure that SRun uses the PMI2 MPI type. And in this line right here is all the magic of benefiting from the work that they do to get that MPI environment to run properly. So you could use MPI run, MPI exec, they just might not work consistently the right way. So learn SRun, and there is a Slurm web page on SRun that gives you everything you can possibly do with it. Okay, so interactive computing. I'll just take a quick moment to mention that. Interactive computing, right now I'm doing interactive computing. I'm working on my laptop. I have an application. It responds to my input, which is my mouse, or I'm typing on the command line. We call that interactive computing. In high performance computing, it's a little bit different. When you use the batch job, everything runs in what we call the background mode. You submit the batch job and say, run my MPI prime code, and Slurm goes, okay, Mary wants 10 nodes, and she's going to do 1 billion up, look for all the primes before 1 billion, and I need 10 nodes for that, and all the cores on all the nodes. And it will wait and schedule and get that whole configuration set up for me, and my job will run in the background. I can go get coffee. I can come back. Oh, is my job done? Oh, my job is done. I'll look at my output file. Okay, that's passive, that's background, and that's great. Batch is built for that, right? Slurm is built for that. But you may need to interact with your data like through a Jupyter notebook to visualize your results. You may have results that are so large you can't download them onto your laptop. It would take a week just to get some of it onto your laptop. It's so big. And so more and more people are needing to run interactive visualization applications, for example. And they do that on a node. You have to be on a login node that's got enough memory and has access to perhaps your large data set on the Lustre file system. And so it has really specific requirements. And so getting an interactive node, you have to do that specially and run a request for that. And here are the two commands. I tested them last night. They both work. Similar versions of these two commands for getting a CPU or a GPU interactive node are in the user guide as well. And I've got the link down here. So you can go to the Expanse user guide. You should be able to cut and paste and make those work, assuming you have your module environment nice and clean. So the srun command will send a request actually to the Slurm scheduler, and you'll wait. You'll sit there and watch, and you'll wait, and it will find a node for you that's available, given the the requests that you want, and you'll be able to run your job. I think there's a limit of 2 hours on an interactive node. I don't know if that's changed, but I didn't put that in here. But you can look on the user guide to find out what it is at this point in time. And you can launch MATLAB Jupyter Notebooks securely from the interactive node. You don't need that. If you use the portal or the portal, it will grab the node for you in the back end and make it a lot easier using the satellite reverse proxy service Galileo client. And we'll talk more about that next week. So here's some examples of using the interactive node. There's my command I submitted. I'm waiting. It's been allocated, and you can tell when you're on an interactive node because it's a different node ID. The host name here is the node name is login2. Here it's expanse-9-55. So I'm going to clean up my environment, and then I just show a few examples. And at this point, I could run the Galileo client script, which we'll talk about next week, and launch a Jupyter Notebook, or I could run ParaView, VisIT. I think there's a session next week on parallel jobs, and I think it includes VisIT. I'm not sure, but we'll have some examples of that. And when you're done, exit, because if you leave it running, you'll get charged for that. Okay, so again, we'll do more of that. Here's an example of getting a similar example. Okay, so here we're getting a GPU node. And how do I know I'm on a GPU node? Maybe over time, you'll get to know the numbers of a GPU node, but you can run the NVIDIA SMI command, which will tell you. If you're on a node, you'll get this kind of information back. Okay, so compiling and running jobs. It's just like other code. You go into your directory where you have an example, and I have an F90 hello MPI example. I check my modules, and if they aren't right, I purge, I reload. And most of our examples, we have a README file that lists the recommended module recipe. And then here I'll compile, because once I've loaded this, I can compile with the MPI F90, and I have a nice new version of Hello MPI. And then I'll submit my job to the Slurm scheduler. Pretty much how it always works. The trick is in this box right here. Sometimes the example, the compiling command can be 3 lines long. It depends on what you're trying to do. And we have an example of that in the user guide for a large compile. And I have that example in my code, my tutorial. How are we doing on time? All right. Well, so okay, we're doing good on time. So I can go through other examples. You can clone them from these different places. Looking in CM shared, you can copy from there. I have some examples expanding on what's in CM shared in this tutorial here. And we have examples for CPU and GPU jobs. So here's an example of an MPI job. Hello MPI.F90. We do have this C example, I think, as well. Hello MPI, I always tell everybody, make sure you have a Hello MPI for whatever language or application that you're working with. The simplest one is indeed just Hello MPI, because if you can compile that and submit a job to the batch scheduler, or try to run it on the command line using an interactive node, there's a whole lot of stuff that we know is working, like your login environment's working, your module environment's working, you can compile. But then if the code doesn't run, like you're developing an advanced code, you've made a lot of changes and it's not working. Well, first of all, if you can run Hello World, you eliminate all the stuff associated with the parallel environment that you need, and you can pretty much guarantee that there's a bug in your code. So, separating out all of the stuff needed to get code to run, all that stuff I've been showing you from your code, that relieves a lot of pressure. You might find that the system's not working right. If your Hello World works every day, and then today it doesn't work, it's not you, right? Unlikely that it's you. And that's a good time to reach out and say, hey, this simple code's not working, and you might find that some service is down. So hello worlds are always great, and then as you progress in your code, develop little hello worlds or unit tests that if this always runs when things are set up right, and it's independent of any current changes you're making in your code, it'll prevent a lot of gray hairs. But we appreciate that the complexity of all these layers, it's really daunting at the beginning. And so having these little tricks given to you is, we hope, helpful. All right, here is simple hello world. I load this is the README file with the module list that we suggest, and then the command, and then run using Slurm or run using the interactive CPU node. Now, this is in a GitHub repository. It was written on a certain date and time. It's entirely possible this command does not work exactly. That's when you go to the user guide, get the most recent command, use it, and then try it. So I guarantee most of this is going to work, but things do change as modules get upgraded, updated, hardware gets added, changed, swapped out. You think of Expanse as one big computer, but it's really a heterogeneous collection of a diverse set of very similar pieces of equipment. But if we bought an EPYC node tomorrow, it would be slightly different than the EPYC nodes we bought at the beginning. So you also have to learn, when to realize it's not you. And so, like I said, try an example in the user guide. If it doesn't work, that example should work, and that's when you would contact and get some help and say, hey, I'm trying this example from the user guide. So either something has changed or you are doing something wrong. So these are really good ways to figure out what's happening. All right, so then here's the list of modules, and I'm compiling in that block. Now here's a batch script. I submit the batch script and I get back, look at this, a whole bunch of hello worlds, and yay, everything is working. I'm printing out the node that the application is running on and the hello world message. And it's a lot longer, so I cut and pasted this. One thing I want to point out to you is that notice these are not in numerical order. That's because all of these processes run on all these different nodes are run asynchronously. And so you can't guarantee synchronization unless you put that in your code. So you'll get used to that. And if you wanted to, you could sort that using a sort command from Unix. All right, OpenMP, very similar. You have the, at this point though, OpenMP is threads based, and what you have to use are the parallel directives. That's the only difference between OpenMP and MPI, and you would want to make sure you have the right compiler command, you compile it, you submit the job runs, and you get out, I changed the output from that one for this example. There is one feature about OpenMP is that you can control the number of threads from environment variables, and this is really essential, is learn to use OMP proc bind, which will bind one thread to like one core. Otherwise, the operating system written for the AMD EPYC processor, they're very brilliant guys, and they make their own decisions about where the threads ought to run. Remember, OpenMP is threads based, so when you ask for 16 threads, it will launch 16 POSIX threads. But by default, you have to tell it where you want them to run. Again, by default, they'll probably all launch on node 0, and the other nodes might be idle. And so if you want one thread per node to do the job and use that node effectively, the core, sorry, one thread per core, then you would bind the thread to the core. You get a one-to-one mapping, and you'll have more efficient scaling. Okay, so at this point, I think I'm done. Here's an example of hybrid OpenMP. It works very similarly from the compiler. Okay, so make sure when things go wrong, check your environment. Do you have the right modules? Purge and start over. What software versions do you need? Did you load those right modules? Does your code compile? Is it updated? You might not have run your code for a year. And in the meantime, the libraries, the busy little bees that keep our system running, have updated and optimized new libraries. Your code won't run. It's possible it won't run, so just recompile if you haven't been on for a long time. Are you running your job from the right location? $home versus $work. And we'll go into that in detail next week. Run it from the right location. You have the scratch, you have the local storage on the node, we have Lustre, and you have your home directory. And again, that will be clearer next week. And then here are some resources, and that's it. So that is the end of my presentation. Are there any questions, or shall we go to the hands-on? All right, let's do a hands-on. Now, I am my training account. I'm one of the people who's linked to the training. Password didn't work, and I still don't have it working. But I'll show you how I log on. And I love to use this command called alias, because you can alias a command. And so when I type expanse, it's SSH-Y, so I can run applications. mthomas at login.expanse.sdsc.edu. So if I'm going to do it manually, I would do SSH mthomas at login. And you guys can try this right now. Open up a terminal if you have it on your laptop. And my password request, I do passwordless access, so I use that SSH off. And I'm on Expanse, I can run the date, who am I? And here's the SQ, and it goes on, and you can pipe it into a Unix command called word count. There's 3,000 plus jobs. Some are running and some are pending. Lots are running. So what you want to do is, well, how many people are waiting? Well, then you would pipe that output into a Unix command called grep, and I would look for PD. Um, Interesting. All the jobs are running, and we have some reservations today, so that's probably part of it. The next thing is I want to get into I want to make sure you can all do this, but at the very hopefully and at the very least use the Expanse portal. So let's get a new window, and we all go to, this is where you guys play along with me. You go to portal.expanse.sdsc.edu, and Cindy or somebody, if you would put that in the general or the chat. I don't know if chat is working. The first thing I'm going to do is get redirected to the Exceed authentication system. So I'll put in my username and password, whichever it is, and then get authenticated, and I'll get redirected back to the Expanse service. So I'll use my portal account, my portal ID and password, which I use a feature called LastPass, which is awesome. If you don't use it, you should learn to use the password manager. And now we're waiting. It can take a while. And now I'm on the Expanse portal. And what's very cool is it's got lots of applications that you can launch by default. And one of them, for example, I can open up a shell. This is called a terminal shell window running on my laptop. But now through the portal, I'm on a terminal shell. And notice it put me in as M. Thomas. I'm now logged into my Expanse account. This guy right here, it's the same if I do an ls, I get my files. If I do an ls, I get my files. This is why the Expanse portal is just so great for simple levels. If I'm in a mode where I'm compiling, debugging, and editing multiple files because they have a big application, then the portal won't work for me, because I work with like 10 terminal windows open at one time. One window for compiling, one window for debugging, one window for or two windows for the different files I'm editing. And so I'm multi-window person, but that's more advanced than just trying to get on and get a few things done or work on a training application. So there's that here, and there's a job composer, and I can also launch, like I said, MATLAB, and I can launch Jupyter Notebooks, interactive application, Jupyter. I'm not going to do that right now. What I want to do right now is stop. At this point, you should all be able to get to this Expanse user portal, and if you can't, speak up, right? So I'm just going to stop share mode so we can all see each other. And if you can log in, and if you can get onto the Expanse portal, put it in the Slack channel that you're good to go, and you can get up, you can leave. But if you're having a problem, hey Kelly, great. If you're having a problem, feel free to raise your hand and ask questions. This is the moment. We've got Mahidar, Marty are here, other people ready to help. And if it's a big problem, we can see what we need to do.